All right, so chapter 5, we look at applying Newton's laws. And the biggest thing is, as I emphasized last semester, was remembering this right here, okay? When we start applying Newton's 3 laws, you've got to remember, is the body at equilibrium, okay? Is it at equilibrium, okay? Meaning what? That you have a constant velocity. If there's constant velocity, that means acceleration is equal to 0, okay? Meters per second squared, all right? So you need to remember that. All right, notice I mentioned your inertial reference frame, or frame of reference. You've always got to have a starting point, okay? Where is our inertial reference frame, okay? Where is it going to be? Is it going to be up here? Is it going to be down on the ground? Is it going to be halfway in between? Doesn't really matter that much. You remember we talking about the jumping off the building, or jumping, remember we had the car jumping the broken bridge, the bridge was out, remember it jumping that ravine? And remember, I think I mentioned this, you could have your inertial reference frame up there where the car was at its highest point, or you could put it down at the bottom. You just got to remember to adjust your signs accordingly, okay? All right. It might have been a little easier to put everything down lower where everything above would have been positive. Okay, you could have done that, okay? All right, so inertial reference frames, it's important to establish where that is and keep it that way all the way through the problem. Don't change positions. Don't change your inertial reference frame halfway through a problem. Don't do that, okay? All right, because you'll forget and get confused. So what does this mean? Anytime you see me write that right there, what does that mean? That means the net force, or the sum of all the forces. A lot of times we physics teachers like to say the sum of all forces, okay? That's what is that, uppercase sigma? Is that what that is? Greek letter sigma? Is that uppercase sigma? Boy, it's Monday, isn't it, y'all? Oh, y'all are kind of like, oh, I don't want to be here. Okay. I feel your pain a little bit, all right? Didn't sleep good. Anybody else not sleep good? Okay, but we're here. We gotta push through, okay? All right, so anytime you see me write that, that means the sum of all forces. So how many forces are involved? Well, it all depends. There may just be one force involved. There could be 2. There could be 3. There could be 10. I think problem number 4 on your homework problem, where you had the car going in 3 different directions? Okay, when we write sum of all forces, we're going to have F1, F2, and F3. Okay? And remember, a couple of those were at angles, and you have to find the components. Oh, man, he's saying that word again. You've got to find the components of all the forces involved. Okay? In other words, there's an X component and a Y component, or an I and J, however you want to say it, okay? So this is very important to get it. And of course, there again, they throw in the sum of the forces into Y and the sum of the forces into X. Okay? And yes, we are going to get into some simultaneous equations. Hopefully do that today, maybe. Okay? Looking at our worksheet I gave you. Okay? So it's important to remember this terminology. Here again, y'all, this is conceptual stuff. Terminology. When you see something that's at equilibrium, or when it's at constant velocity, or when it's not accelerating, then what is my sum of my forces going to be equal to? That right there. That is super important, because if it's not, then that equation changes right to this right here. Okay? Now again, remember, what all forces does that involve? That is frictional force. That is tensional force. That is weight. That is normal force. A force is a force. Do you understand me? So that sum of all forces literally means all 4 types of forces. If they are present, they will go there. They will not go over here. What goes over here? If it's accelerating, MA. If it's not, 0. Okay? Now you say, well, boy, that's fundamental. That's just easy, easy as pie. Well, okay, but let's remember that. Because when we start writing these equations out, you're going to say, Mr. Shields, why is it equal to 0? Well, it's not accelerating. Well, Mr. Shields, this one's equal to MA. It's accelerating. Okay? All right, and that's super important to remember. Okay? Please, 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 please. All right, now, you can write this down now. Look, everybody, do you have to go step by step? Well, I'm going to tell you right now, you better draw the sucker. Okay? You better draw it and you better label it. Label all your forces. Is it accelerating? Which way is it accelerating? Draw an arrow and put accelerating, 2 meters per second squared or whatever. Okay? Show where gravity's at. Okay? Please draw it and label it. Okay? The free body diagram, of course, is important whether it's whether it's in equilibrium or not. Okay? You've got to have that free body diagram. Okay? And then, of course, begin to ask yourself these questions. Okay? Notice if mass is given, weight will come into play. Okay? All right? And basically the weight is the normal force. If an object is on a flat surface, the weight of the object is the normal force. If it's on a tilted surface, the weight of the object is the normal force cosine theta. All right? You got to throw in cosine theta. You'll see what I'm talking about when we draw these problems, okay? And then, of course, check and then choose a set of coordinates. Oh, man, did you hear that? Always put a set of coordinates on there somewhere, which is going to be x, which is going to be y. Even when it's tilted, you still need to have that x. Typically, x always follows the surface that the object falls on, what it's resting on. If it's tilted up, guess what? You tilt your x up. And your y is this way and that way. Okay? You'll see what I'm talking about when we draw them, all right? Okay? Any questions? And then, of course, execute. And I'm going to put this in the video just if somebody wanted to go back and look at it. It's in your textbook. I mean, I don't even need to record it. It's in your textbook on page, page 131, the problem-solving strategy, 5.1, okay? So you can go back and look at it there. Always evaluate your answer. Does this make physical sense? Is it in the proper dimensions? Here's another one that causes us to stump our toe every now and then. I'll be grading papers and somebody will get the wrong dimension. And that's an easy thing, but it can, you lose track of where you are and you put the wrong dimension. You put meters per second when it ought to have been meters per second squared when it ought to have been newtons, or kilograms when it ought to have been meters per second squared, or you got to keep everything dimensionally correct. And does it make physical sense? I mean, come on. If an object is accelerating down a ramp at say 1.5 meters per second for a time interval of 1.5 seconds, and you get a final velocity, it starts from rest, and you calculate the final velocity of the object after it falls or slides for 1.5 seconds, and you get an answer of 30 meters per second. I mean, come on. Okay. You know that's wrong. There's no way, with an acceleration of 1.5 meters per second, after 1.5 seconds, you're going to get a final velocity of 30 meters per second. So, remember what velocity is. Remember what acceleration is, okay? You can do it in your head, and you'll say, that's something's wrong. There's no way, okay? All right? All right, again, now, what if the net force is not zero? Well, I just wrote this. Okay? So sum of the forces is equal to zero is when it's net force zero, acceleration zero, constant velocity. You with me? When it's accelerating, that's how you write it. Now remember, you say, well, Mr. Shields, that's just F. Remember what all F is. Tension, weight, normal force, frictional force. We can have a big, long equation over here equals to MA. Okay? And we are. It's going to come to that. And I say big, long, I don't mean, this long, but, it's going to have several parts to it, okay? All right? Okay. I gave you some on your worksheet that fall right along with this, okay? Okay? So what's the key here? And how do I need to write this on my formula sheet? When it's not in equilibrium. You got to put that MA to the right. Okay? And that's really all you need out there is the MA, period. Okay? Now, can that mass be a total of several masses? Yes, it can. When you see M, if you've got three objects accelerating down an incline, then guess what? The mass of those three objects have to go over there. Okay, so just because it says M doesn't mean one M, it means total M. Okay? I mean, you ought to know that, but I just want to make sure you know that. All right? Just want to make sure. All right? Okay? All right. Of course, they're talking about here, notice here, MA doesn't belong here. Why? Well, because of gravity. So instead of saying MA, we could say what? MG, couldn't we? Okay? So how would we draw this? This would be one way to draw it. You draw your weight. What is weight? What is weight, y'all? Mg. And it's accelerating downward. So now notice my arrows. Now later on we can come in here and draw another arrow going up, can't we? And what would that be?
Air resistance.
Air resistance, absolutely. Okay? I mean, that's just commonsensical, right? Because you know as an object falls, there's air resistance in the opposite direction. That's a frictional force, isn't it? Can be. It could be. It could be. Okay? All right? All right, so this would be the proper way if I were to give you a simple problem and say, all right, that's what you're, of an apple falling. That's how you would need to draw your free body diagram, just like that right there. Okay? Okay. All right? Okay. Notice, too, you don't draw both vectors the same length because the acceleration of the apple will not match the weight of the apple. Because what is the acceleration of a falling apple? G. Yeah, period. Weight is mass times G. So your arrow should be longer for the weight. Now y'all listen, I'm not going to get out a transit and shoot points here or a compass and say, oh, his arrow was 2/3 too long. Okay? Just make it noticeable. All right? Just so you know. All right? Now I will say this, if the forces are equal, the vector length should equal. You got two objects and they're moving in the same direction with the same force, then the vector arrows should equal. Now y'all, I'll be honest, sometimes I don't follow that rule exactly like I should. I get a little careless. I get in a hurry. So if you call my attention to it, that's fine. But, the biggest thing is draw it, label it. That's the biggest thing. Okay? All right? Okay. And again, this is for dynamics. Okay. If you want to write this down, you can. This is... yeah, I think this is page, this might be page 131. Once a minute, yeah, okay. No, excuse me, no it's not. 136. This is on page 136. So if you want to, you can write it down or not, page 136, it's listed for you. Problem solving strategy 5.2, okay. Again, always draw your free body, label your weight, choose your XY coordinates, and come on y'all, if an object's falling, typically we got what? This is Y and this is X, right? I mean, that's just common sense, okay? All right, let's move on. And then, of course, execute. Again, does it make physical sense? All right, if an object falls for 2 seconds, it should not have a final velocity right before it hits the ground of 100 meters per second. After 2 seconds of fall, no way, Jose. All right? You punched in the wrong number, you moved the decimal too far one way, something, okay? Again, does it make physical sense? Please always ask yourself that. If you're not, always go back and look at, does this make physical sense? Work the problem backward if you have to. Okay? Take what value you get and see if you get one of your known values. If you don't, you've worked it wrong. Okay? I used to work problems backwards all the time. Sometimes I still do. I'm like, let me work this backward. Let me see if I can get this if I work it using what I got. Okay? You do that in math all the time. All right? My math teachers always told us, work it backwards. If you're not sure, work it backwards. Okay? That really helps you to learn it. Okay? All right, what the heck? All right, now let's look at frictional forces. All right, we've already briefly talked about frictional forces. Okay, so frictional forces, remember that frictional forces are in the opposite direction, right? Okay? Opposite direction. Frictional forces are always going to be opposite in direction. Okay? They have to be or they wouldn't be frictional. Even kinetic friction. Now kinetic friction is much less than static friction. Okay? What's an example of static friction? Oh yeah, my posters. How in the world are they hanging up there? Well, I cheated. They're not tape. Well, they're partially tape. Oh, no, that one's push pins, which I'd rather hang them that way, but push pins won't go into concrete, right? Okay, so how are they hanging? Well, I got Velcro with a little adhesive on the back. So, let me ask you something. Could I hang a bowling ball on that piece of Velcro? Not that piece. Yes, very good. Yeah, if I had a big chunk of Velcro, I probably could. But not that one. Why? Well, okay, it's pulling straight down, right? Well, the frictional force is going to be which way? Opposite, right? So, my static frictional force here is greater, and of course I have more than one. Now, if I just use one piece of Velcro, you think it might hold this poster up? Might be a little iffy, wouldn't it? Probably would, but a little bit of air come through the room, the wind blowing, air currents in the room, it might cause it to fall. But I've got one at each corner in the middles, okay? So, man, it's not coming down, hopefully. Okay, are they in the middle? Yeah, right there, about middle. So what I'm getting at is you've got static friction. Come on, y'all, you're going to take statics when you get to engineering school. Have you already taken statics? Have you taken any statics yet? It's coming, okay? Well, that's what we're going to be dealing with, okay? Except it'll be a little more involved. You'll have multiple angles, but again, if you draw your free body diagram, if you label it properly, you keep all your angles and everything correct, it's doable. I'm telling you, statics is not as bad as it seems, okay? You just, again, got to keep everything labeled, keep up with all your directions, your angles, and then work it out, okay? All right, now, so the static frictional force is greater. However, with the bowling ball, with this piece of Velcro, it would not be, because the weight of the bowling ball is going to be much, much greater than the frictional force, the static frictional force. Tape on a wall, glue. How do they know that glue is going to hold that dude up from that steel I-beam when he sticks his hard hat on it? You ever seen that video of the old super glue commercials? When they first come out with super glue, that's what they'd do. They'd demonstrate. They had a guy way up off the ground. He had on a hard hat, had it strapped around his head, and he'd put some super glue on there, had a little thing on there, and put some super glue on it and go to a steel I-beam and leave him there he'd hold it about 10, 15, 20 seconds, and he'd let go, and he'd wiggle around, and it would not break. That stuff's powerful. Well, how do they know that? Well, good chemistry. The chemists know they created that glue to have a very high tensile strength in the bonds. Okay, we get into some organic chemistry here. Okay, because remember, what are bonds? Chemical bonds. Well, they're forces, y'all. That's all it is. It's electrostatic force, okay? And some tensional force, too, in the compound once it hardens, okay? And so that's how they know. Static force. All right, so static force. Do you want a high static force on your rubber tires when you're driving down the road, especially if it's wet? Do you want it to stick, grip the road? Yeah. Bear claw, right? Okay. Yeah. Because what happens if they get worn and it's wet and you just tap the brakes? What do? Fishtail, don't you? And you know why? Because now you've gone from low static friction. So you don't want static friction on your tires to get low because they're not going to grip worth a flip. All right? Same thing if you're working, say, at chicken plant. Okay? All right? Those guys, they wear a certain kind of shoes. They're rubber sole shoes. Why? Because the floors are wet. And there's tile. And you don't want something you're going to go in there and bust your tail and, get hurt and be out of work for 6 months. Okay? Or any other place where there's a lot of running water. Okay? Chemical plant. There's a lot of water around. You don't want to be cement plant. You don't want to be slipping and sliding everywhere. Static friction is what you want. Kinetic friction, however, is friction that occurs while an object is moving across, rolling, or sliding across the surface. So our static friction is very low. It's always lower than, our kinetic friction is always low. It's lower than static. It has to be or it wouldn't slide. You follow me? Why do cars have anti-lock brakes? Now, old cars, my old 67 Chevy, it doesn't have them. Okay. Why? Because you don't want to do what? You don't want to what? It's to prevent what? Skidding, right? Why? Well, you actually accelerate for a brief moment when you go into a skid. Have you ever noticed that? Have you ever been in something, you go into a skid, you ever feel your body kind of pull backwards? Well, it's because you're accelerating. You don't want to accelerate, okay? Heaven forbid, if you're trying to keep from hitting another car, the last thing you want to do is gain speed. You want to lose speed. You want to slow down. You don't want to accelerate, okay? And that's why they build those anti-lock brakes. And I love them too, by the way. Because these older cars, that old Camaro I had in high school, it liked to slide when I hit those brakes, especially when it was wet. Had to be really careful, okay? Going through a curve. Out at my house, there's a curve in the road right before you get to my house. And I would hate to know how many wrecks have been out there since we've lived there 11 years. And they've paved it, and it's still slick. People slide off and hit the trees. So, kinetic friction. Okay, so here we go. More equations. More equations. We're fixed to stop here in a minute. What did I do with my pen? Oh, there it is. Okay, more equations. Equations for friction are very simple. Notice that they're the same. Coefficient of kinetic and coefficient of static. Now notice this right here. Kinetic force is equal to, what is this right here? Mu is the coefficient How do you spell coefficient? Yeah, C-O-E-F-F. Thank you. Is that right? Coefficient? Coefficient. C-I-E-N-T, right? Coefficient. There we go. This is a coefficient of kinetic friction, and this right here is a coefficient of static. Mu of K, mu of S. Real simple, okay? Real simple. Sorry about my spelling. I just get mental blocks sometimes with words, and I freeze up. Sorry, okay? All right, so static friction is when there's no motion, and it's really simple, y'all. And kinetic is when there's motion. That's the simplest way to remember it, okay? So here's an equation. Notice they're the same. The only thing that's different about them, of course, is your coefficient is going to be different. And notice this right here, equal to or less than. Equal to or less than. This is always equals to. Okay? Coefficients of kinetic friction are lower than mu of S. Okay. Just give you an example. A rubber tire. Its coefficient of static friction might, I'm just going to use a nice round number, 1. Okay. But the coefficient of kinetic friction of that rubber tire might be 0.3. And it is unitless, by the way. The coefficients are unitless. Okay. All right. Okay. Does that make sense? Let me ask you this. Can you have a coefficient of kinetic friction, coefficient of static friction greater than 1? Yes. It was believed for a long time and taught for a long time that coefficients of kinetic friction, coefficients of static friction could not ever be higher than 1. Well, that's not the case. Have you ever gone to the drag races? You ever watched drag cars? You ever notice how those tires grip? Boy, I mean, they grip that pavement, don't they? The tire literally starts twisting around the axle, doesn't it, if you watch it in slow motion? Well, how in the world does it do that? That rubber, for one, they get it hot. That's why they do that fire burnout. They used to use Clorox solution on those tires because it helped the rubber grip a little bit better, but then they didn't think about it. They were producing chlorine gas at the drag strip, and people are getting sick. You know, especially the guys working right there around the burnout area. And so they quit using. I remember when you go to Green Valley, Balenton. I always went to Balenton a lot. You could smell that chlorine, boy. And we were sitting way back. And then they quit it. They outlawed it. Because, look, you're making chlorine gas, man. And Chlorine decomposes really easy. You know that from chemistry. So they just use water now, and it works pretty much just as well. They make that tire real hot and sticky. You know what happens to static friction coefficient? Goes through the roof. Probably goes to maybe 3, maybe even higher. Okay? So if you think about it, what is that doing? If you have a coefficient of static friction of 3, then basically what you're doing here, and by the way, that's the normal force. You're taking the normal force and multiplying it by 3. Well, that's what you want to do if you want to start quick, don't you? That relays back into torque. Okay? You want it high, so you get off the line quick. Okay? All right. Okay? Any questions? All right. So please do not, let me back up. I don't know if I stressed that enough. Please do not forget that that little N right there is the normal force. And how do we find normal force? All right, look, y'all. Normal force. Okay. Well, how do I find a normal force? mg. So F of N, now remember I told you I like to write it this way. That's normal force, is equal to mg. And so how would we write these equations? Watch. F of K is equal to mu mg, mu of K, and F of S is equal to mu of S mg. Okay? That's how you write them. All right? Okay, any questions? Okay. I'm going to stop right there. I think that's a good stopping point.